So continuous time Markov chains can have stationary distributions, and we're about to look into what that means. The first thing we're going to do is require that pi, which is going to be a stationary distribution, or is going to denote one, better be a distribution itself. That means that every pi x is not negative. That means that the pi x is summed to 1. That's what it means for pi to be a distribution. And both of those imply that the probabilities, the pi x's, are actually probabilities, meaning between 0 and 1. And so, every continuous time Markov chain, a homogeneous one, is associated with these transition probabilities given for all pairs of states and all times t. And really, in a sense, defining a stationary distribution is pretty simple. You go after these two conditions, and if you can verify either, you're in business. This one, local balance, is going to correspond to naturally reversible continuous time Markov chains, as was the case in the discrete time setting, and global balance is the one that you would check next. And if you cannot verify either, then you don't have a stationary distribution for that particular continuous time chain. You can see that these conditions are a little bit cumbersome. They're not going to be very convenient to verify, and that's because these probabilities are typically very complicated. They're also defined, not just over all states, but for all times t. So it's a bit of a headache to actually verify these conditions, even though they kind of paraphrase our intuition from the discrete time setup. And so what we'd like to do is in fact borrow a little bit from the discrete time setting and use our notion of one-step transitions, namely the generator, over in continuous time. So let's see how we can do this. We're going to start with the definition of global balance for a continuous time Markov chain. So this is the kind of main condition that's going to guarantee for us that that pi is a stationary distribution. So you start off with this condition, and now what we're going to do is we're going to take a derivative with respect to t and apply the Chapman-Kolmogorov equations, which we've seen already. And so that's exactly what we're going to do. The left-hand side is going to turn to 0 because it doesn't depend on t. Let's see how this all works out. So again, we pick up 0 on the left-hand side. In the right-hand side, the derivative goes past the pi x and is just going to differentiate the thing that depends on t, which is the transition probability. Once you kind of have this, you apply Chapman-Kolmogorov. So all I'm doing in the next step is substituting this expression here. So there it is, right there. And now it's just a matter of simplifying a little bit. So one thing that you can do is put the pi x inside the sum. In fact, you switch the order of the sums. So I'm going to put the pi x in, and then one of the sums, namely the one that sums over the x, is not going to depend on z, which is going to allow us to kind of exchange the order of summation and pull out the RZY, the generator from state z to state y, or the rate from state z to state y. And now what you notice is that this expression right here, and that I'm putting in a box, is just equal to pi z. And the reason for that is because we're just applying global balance to state z. So here is the global balance for state y, and it holds for all states, so it definitely holds for state z. And so all this sum is being replaced by is pi z, which gives us a pretty simple condition. Here it is written out in full form. We've seen by now that homogeneous chains are defined by their infinitesimal generator. So this is all we're given, and this is all we need to verify that some distribution function pi is indeed a stationary distribution for that particular chain. This condition would need to be verified, and this condition is coming directly from the previous slide where we started at 0 and ended up at the quantity on the right hand side here. There is one kind of quick sort of substitution that's going to allow a bit more interpretability for this equation. So we know that the generator entry for yy is just the negative rate at that particular state, which is then going to allow us to rewrite the above condition like so. And this is much more memorable. First of all, it looks a little bit more like the discrete time case. And second of all, it has this interpretation of being a conservation law. If you look at the left-hand side here, we see the probability of staying in state y after a long time. That's what a stationary distribution is supposed to represent, times the rate of leaving state y. So ry is the state at which we jump out of that particular state, and that's what you see on the left-hand side. On the right-hand side, you see a sum over all x's, which is going to be a multiplication of two terms. One is the probability of being in that particular state, state x, times the probability of transitioning from state x to state y. Not the probability, but the rate of transitioning. So you see that there is sort of a conservation going on. You have the likelihood of being in state y times the rate at which we leave, which is being counteracted by the probability of being in any one of the other states with the rate of coming back into state y. So there's a really nice interpretation here that has the same type of character as we had in discrete time. The very same set of steps, namely differentiating, applies to local balance, so it's an even simpler condition, and it's also a type of a conservation law. It says that the probability of being in state x and then transitioning to state y is the same as the probability of being in state y and transitioning to state x. So there's a conservation of flow that's happening in both of these equations. And of course, we know local balance corresponds to time reversible processes, and global balance is just kind of the more kind of mainstay condition for the existence of a stationary distribution. So quick note on something that we've been calling the stationary measure. In other words, if you want to find the function pi, the stationary distribution of a continuous time Markov chain, you can try to instead find any non-negative function mu satisfying either global or local balance. And then once you've found this, then you can just normalize it so that it's a proper distribution. That's what this step is about, to get, not surprisingly, the stationary distribution. So, this is usually kind of more amenable to practice, in the sense that you don't want to look for a distribution right away. You look for a function mu satisfying global or local balance, and then once you're done finding it, then you just normalize it by the sum, and that way pi has the right conditions. It's not negative because mu was, and it sums to 1 just by the nature of this definition. If you sum up the numerator, it cancels with the denominator, giving you a 1. So that's just a bit of kind of practical advice. And then the final thing I want to say about the stationary distribution of a continuous time chain is to kind of talk a little bit about the relationship to the embedded chain Z. So we know that x is specified by the rates of that dictate how long we wait in each one of the states, and then also the embedded one-step transition probabilities that tell us where we move from any one individual state to another. And so, it would be interesting to see what the connection is between the stationary distribution of a CMTC and the stationary distribution of its embedded chain. So here, I'm going to let rho denote the stationary distribution, or in fact a measure. So rho doesn't have to be normalized to sum to 1. What I'm going to show you will work regardless. But once you have this rho, let's define our pi like this. And what we're now going to do is try to check that this expression gives us the right thing, namely the stationary distribution of x. One thing before we do so is just to see if this quantity makes sense. So the stationary distribution is supposed to let us know of the probability that once time runs for a very long time, where is the most likely location of the chain x. And what this is saying, if we look at the numerator, is that the likely position of the chain x is determined by two things. One, it's determined by where the embedded chain is likely to be. That's the rho x term. So that makes a lot of sense. The embedded chain is gonna, should have some say about where the continuous time chain will be. So the more likely the embedded chain is to be in state x, the more likely it is for the continuous time chain to be in state x. And then you see a division by Rx here, which is also reasonable. And the reason for this is, let's think about what Rx represents. Rx is the rate of leaving that particular state. So if R is very large, we tend to leave that state very quickly. And that's why the division has quite a bit of intuition around it. When Rx is large, it's saying that the probability of finding the continuous time chain in state x is going to be small, right? Because it just jumps out too quickly. Conversely, if Rx is small, so a small rate corresponds to a long waiting time, a long kind of length to one of those steps in the diagram below me. So we wait in that particular state for a long time. And that corresponds very well with our intuition of how likely we are to find the continuous time chain in state x after a long time. If it tends to wait there, to linger there in that state for lengthy periods of time, we're just going to be more likely to find it there. So now let's see if this intuition holds water. So let's go step by step. The first is, let's check pi is an actual distribution. And this is easy. So every one of these things, every one of these terms is non-negative. That's clearly true. They clearly sum to 1, because if you sum up the numerator, you get exactly what's in the denominator. So pi, as defined here, is in fact a distribution. The next step is a little bit more complicated. What do we need to establish that pi is a stationary distribution? We need to satisfy the global balance condition. And so the global balance condition, let me just very quickly backtrack. The global balance condition that I'm going to try to verify is this one, right here. So we're going to start off with the left-hand side and hope that eventually we get to the right-hand side. Let's see how this works out. This is my left-hand side, and what I'm doing is simply plugging in this definition here, with the exception is that I've replaced the x by the y, and because of that, the rate ry for state y cancels out. In other words, pi y is equal to rho y divided by ry, and the ry cancels. So that's step 1, which is a kind of an immediate cancellation of ry. The next step is using the fact that rho is a stationary distribution for z, and therefore satisfies a global balance condition of its own. However, that's going to be with respect to its one-step transition probability. So z is a discrete time Markov chain. It has one-step transition probability bxy's, and so what I've put it there in the numerator is precisely the global balance condition for the stationary distribution rho. Okay, now that if we're past this step, we're going to try to get rid of the bxy's because that's related to the embedded chain. We're going to replace them with the rates of the continuous time chain. Rxy is equal to Rx times bxy, and that's all I've plugged in there to get me to this step here. So I've divided by Rx, and I have the right, that's how I get the next step. And at this point, it's not too difficult to see that we're actually done. So why is this? Well, the pi x that you're seeing here is in fact everything in this quantity above, except the transition rate rxy. If you look at the definition of pi x up here, you'll see all of the terms, the rho x, the rx, and that divisor there. So we've kind of pretty cleanly gotten to the end of the calculation, and this is sort of the summary. The summary is that if you have rho be the stationary distribution of the embedded chain, and you define pi, some function like this, provided of course that the denominator is summable, then pi will represent the stationary distribution of x, and this is true because we verified this global balance condition. There is one more kind of consequence that you can work out on your own. It's sort of the converse to this statement. If pi is the stationary distribution of x, then what is the stationary distribution of the embedded chain? Well, it's rho given as such, which is not terribly surprising. It's just the fact that this quantity here, this rx, switches over. You multiply both sides, and you get this proportionality, and the denominator there is just responsible for normalizing this function rho so that it's indeed a distribution. So you have both of those formulas. There's nothing too complicated here, and the condition, let me come back to global balance very quickly. The condition for global balance is quite intuitive, and this is all you have to verify given the generator of a continuous time Markov chain to arrive at its stationary distribution. Okay, that ends this